Hi, this is section 4.2 area, and what we're doing is we're computing area using an infinite number of rectangles, and we're figuring out the area of each one of those rectangles, and we're using what's called the limiting process. And I'm going to go through a number of examples. This is the very first one I introduced at the very beginning of this section, and I believe I did it with 5 rectangles initially and then 100 rectangles, and now I'm going to do an infinite number of rectangles. So this is how you start out. You first figure out what delta x is. Delta x is b, which is your largest interval number minus your smallest interval number. So b minus a over number of rectangles I have, which is n, because I have an infinite number of them. So my delta x is going to be 2 over n. And then the next thing I figure out is I figure out c sub I. And c sub I is my incremental change along the x-axis to give me my different heights as my function changes from x to x. And that is computed as a plus delta xi. So in this case, c sub I is going to be 0, because that's my a value, plus 2ni. And that's what which is simply 2i over n, and that's what I'm going to substitute in that particular function. So now I'm going to start taking the limiting process. I'm going to take the limit as n goes to infinity, which means I have an infinite number of rectangles, and I'm going to add all the areas of those rectangles from 1 to n, and I'm going to substitute into my function c sub I, so that's going to be 2i over n, and I'm going to multiply that height by the width, which is delta x, which in this case is 2 over n. So if I continue on this, I have the limit as n approaches infinity of the summation of I equals 1 to n, and I've got a bracket here for my function, and it's going to be a negative 2i over n that squared plus 5 times my width, which is 2n. And that is equal to the limit as n goes to infinity of the summation of I going from 1 to n, and in this bracket I'm going to have a negative 4i squared over n squared plus 5 all over 2 over n. So if I continue this, I now have the limit as n goes to infinity, summation of I equals 1 to n, and if I distribute this, I will get a negative 8i squared over n cubed plus 10 over n. And so I'm going to break this up into 2 summations, and I'm going to write it up here, I think. I'll get myself more room if I write it right here. And so I have the limit as n goes to infinity, and my first summation will be a negative 8 over n cubed times the summation of I equals 1 to n of I squared plus 1 over n times the summation of I equals 1 to n times 10, of 10. Alright, so now I can do my substitution of my explicit representation for the summation. In other words, I'm going to have negative 8 over n cubed times n squared is n times n plus 1 times 2n plus 1 all over 6 plus 1 over n times, again I multiply these two when I have a constant, so I have 10n, and this is going to give me the limit, and now I'm going to do some simplification, and over here this n and this n cubed is going to simplify, and this negative 8 and this 6 is going to simplify, so I'm going to have a negative 4 times n plus 1 times 2n plus 1 over 3n squared plus, well, here this is like 10n over 1, so these n's will simplify, and so I have plus 10. Okay, I can simplify this a little bit further. And the limit as n approaches infinity of a negative 4, I'm going to FOIL this, and I'm going to have 2n squared plus 3n plus 1 over 3n squared over here plus 10. And I'm going to distribute now that negative 4. And I'm going to have a negative 8n squared minus 12n minus 4 over 3n squared plus 10. Now the degrees are the same, so I'm going to use my leading coefficients right here. And when I take the limit of this, I'm going to get a negative 8/3. When I take the limit of this, I'm going to have 10. And that's the same as a negative 8/3 plus 30/3, which is 22/3. And I get 7 1/3 as my area. All right, that's my answer for example 1.